We're continuing our study, our look at finding limits analytically. Just wanted you guys to know that I didn't produce this as a handout for you guys, so using your own notebook paper, go ahead and just put this title up there on a particular piece of paper that you're using. Don't worry about your name, of course, the title, don't worry about that. If you've got it labeled as such, maybe with the particular date, then you're good. All right, let's look at our first example of finding a limit analytically. First of all, we want to evaluate this function at 1. So when we do that and plug 1 in, we get 0 over 0. It'd probably be good to show that. That's what we call the indeterminate form. Now, if we were asking the question as far as what's the functional value at 1, then my answer would be undefined or does not exist. But we're working in the context of limits, so the point may not be there, but the limits may still exist. Okay, so we need to do some further investigation is what this means to us when we're dealing in the context of a limit. All right, but I think I would show this right here, that this is 0 over 0. Now, prior to today, what you would have had to have done is type this in the calculator, investigate the behavior near values that are close to 1 on either side of it, and notice what the y values are doing. Look for the structure and make use of it. See if your y's are going to a particular number. Build a table of values, if you will. But we want to start moving away from that. It's good to know that as an option, but what happens when we get 0 over 0 and how should we proceed if we don't have a graphing calculator to utilize? All right, in this case right here then, what we want to do is I'm going to go ahead and say, you know what, I've got to begin the problem over again. So when I look at the problem right here, I think, well, I've got to do something else because I'm going to still get 0 over 0, so we're going to try and factor the numerator. All right, factoring requires that we remember from pre-cal, and you've got the polynomial review in your pre-cal notes if you want to look it up. Factoring requires that we remember how to factor a difference or sum of 2 cubes. Okay, and from pre-cal, from Algebra 2, what that means is that when we subtract 2 cubes, we fill the binomial, okay, with the cube roots of each of the terms, so a minus b. We keep the same operation sign that's between the 2 cubes here. So had this been plus, we put a plus here. To build the trinomial, what we do is we take and square the first term, whatever it may be. We square the last term, which is also b squared, positive. We take the 2 middle terms and we take the 2 terms here, multiply them together, take the opposite in sign, okay, and that's going to be our middle term. So this is going to be plus the product AB. So again, like I said, you have prior notes that would help you review sum and differences of 2 cubes and factoring into a binomial times a trinomial. Okay, so real quickly applying that formula over here, looking at the numerator, and we know it's a binomial times a trinomial. And it'd be very helpful if you think about it a step ahead that if this binomial was x minus 1, I'd be able to cancel with the x minus 1 in the denominator, which is causing the division by 0. So in fact, that's how it works out. The cube root of x cubed is x, and the cube root of 1 is 1. Okay, building the trinomial, the square of the first, square of the last, plus 1. Multiply the 2 together, and find the opposite. So that product is negative x, its opposite is plus x. Okay, again, notice that right here, I retained the limit expression, so I'm just going to kind of come back here and put like, this implies that I'm doing this next move. Next, cancel. Maybe clean it up. Some of you guys are going to be able to skip this step right here and it won't bother you, but it does show a nice flow here. Okay, now you're able to evaluate this function at 1 without any problems, plug it in, and you get an answer of 3. So our limit is 3. Okay, so a little more algebra, just a little more intense, not just factoring, basic functions, but more involved as far as difference of 2 cubes. Okay, let's look at example 2. All right, let's evaluate this function at 3. Let's go ahead and try direct substitution. Let me go ahead and plug 3 in, and when I do, notice I drop the limit expression. Evaluate at 3. Let's see if there's any issues that are raised. We certainly don't want a negative. Well, no, I guess it'd be okay to have a negative number underneath a cube root. Okay, it's just the even roots that you wouldn't want to have that in. So it looks like we're going to be okay here. 9 times 2 is 18. 18 minus 10 is 8, so it becomes the cube root of 8. Nice. That's equal to 2. So nothing interesting there. Just maybe the cube roots. Okay. Third example here. Go ahead and quickly plug in 0 and see what happens. Okay, when you evaluate this at 0, okay, this function, you're going to get the square root of 5 on top, minus the square root of 5, which is 0, and then this would also be 0, 0 over 0, indeterminate. At this point, prior to today, you'd have to go to the graphing calculator, type this function in, investigate behavior on either side of 0 to determine what the y values are doing. Okay, but after today, we have another strategy. All right, so rewriting the problem. Okay, notice that you can't really factor, per se, the numerator. So we have to come up with a different strategy here. And you might remember one of the videos that you watched at the beginning of the year. I think it was the cartoon type video of limits, where he was showing how to solve limits, explaining how to solve limits analytically. Well, this kind of ties into that. All right, we get 0 over 0, so we have to come up with some other kind of strategy. Well, what we're going to do, since factoring really won't work here, is when I see radicals, just think of this as an option. I'm going to multiply this expression right here by an equivalent form of 1 so that I don't change the value of this function. I'm going to multiply by 1. But I'm going to multiply by the conjugate of this numerator. You might go, well, what was the conjugate again? Well, it's actually the entire expression, but with an opposite operation sign. So where this is subtraction, you're going to change it to addition. And remember, we had to multiply by a form of 1, so what we build the numerator with, we need to also put in the denominator because those cancel to a 1. Okay? So we're multiplying by the conjugate, okay? But just kind of wait for the big picture here and see in a second why we would do that, okay? All right, coming down here on your next line, retaining the limit expression. I haven't substituted in 0, so it has to stay there. Okay, let's come back to the problem and do the necessary algebra here. If I multiply these two terms together, these two terms right here, multiplying them together, notice that these two first terms are alike. These last two terms are alike, so we have the sum and difference of like terms. FOIL it out, but know that your outside and inside are going to eventually cancel. So really, it's just the shortcut method, and here we get x plus 5. We multiply these two together, and we get minus square root of 25, which is just 5. I see in my next step that these are going to clean up and cancel, so I'm left with x on top. But let's move to the denominator here and do the algebra here. So I've got x. Do not distribute this x inside both these terms. You can, but you're going to eventually have to end up factoring it out. Okay, notice what I've done in the denominator. So the numerators I multiplied together, the denominators I leave in factored form. Okay, and here's why. If you were to cancel these and know that you're left with x on top, notice that that x divides with that x. So x divides out leaving 1, x divides out leaving 1. Think about that you just got rid of the whole situation of dividing by 0. Very convenient. So I'm going to clean it up with another limit statement, and then I'm going to evaluate. Okay, the situation of division by 0 is gone now that I've divided out the x, canceled out the x. Now I'm going to evaluate at 0, so think about what we have. I'm going to drop the limit statement. This is 0, so I have the square root of 5 plus the square root of 5. And collecting like radicals in the denominator produces 1 over 2 root 5, because each of these are 1. And when I collect them, I have 2 of them. Do you have to rationalize? No, not in this course. We're good to go. Rationalizing has its place, but not right here. Okay? All right, so that's the technique that you may have seen earlier in a previous video. And that's just one more thing that you can do. If factoring doesn't work, think about the technique of multiplying by the conjugate. Just make sure that your notation kind of follows nicely and in C. Okay? All right. The next two examples are going to take a little bit longer, probably 10 minutes total, 5 minutes at least a piece. So I'm going to stop here and put it in a different video so that it all works out fine. So I'll see you in just a second.